So in this video, I'd like to go over the solutions to the gas loss quiz. So the thing is that there's actually 4 different versions of the gas law quiz. So I'm going to alternate between the versions. Just realize that every question is analogous between the versions. All right, so for example, this is for the question number 1, I'm going to use form B. All right, if you look at the question on your version, the words are basically the same. It's just there's a few changes, and if you follow the same method, you should be able to get the answer. All right. I'm just going to I'm going to alternate between the versions, but I'll give the answers for all the different versions, and that way you can check to see whether or not yours was correct. Okay. So again, this is from Form B, question number 1. All right, the first thing that you would have to do is to balance the equation, and the equation is the same for all the versions, so it should be 2, 1, 2. All right, so it says if you get 1.53 moles of oxygen, all right, and it combined with hydrogen at standard temperature and pressure, what volume of water vapor would be formed? So the first step is that you need to do a one-step crossbar where you convert moles of this material into a number of moles of water. All right, so some of the versions have oxygen, some of the versions have hydrogen, so you have to do a mole to mole comparison. If this were to have said hydrogen here, this would say 2 moles of hydrogen down here. So I think that's the way it is on some of the versions. All right, so you're going to calculate a certain number of moles of water. All right, so whatever that number of moles is, all right, is going, there's actually 2 ways that you can do this. You can use PV equals nRT, because we would know a pressure, volume, or sorry, there's going to be a pressure, a volume, an amount of moles, a gas constant, and a temperature there. All right, so if we rearrange this equation right here, the N is our number of moles. That's going to be this right here. All right, to get our R, remember we want to look at pressure. All right, we want to, you pick one that corresponds to certain units of pressure. Since we're doing it at standard temperature and pressure, we could choose any of those units of pressure. All right, I just happen to use millimeters of mercury. All right, so 760 millimeters of mercury. So therefore, I'm going to use this version of R. All right, I could have done this with atmospheres down here and just used that particular unit of R. All right, this is the temperature for standard temperature and pressure, and I would end up getting this number right here. The other way that you could do this is to realize that this is a gas at standard temperature and pressure, and if you have a certain number of moles, all right, remember that for any 1 mole of a gas at standard temperature and pressure, it is 22.4 liters. All right, and so you could do this. Actually, this part right here is something that we would do. You should have been able to do from the stoichiometry unit, and notice that you basically get the same number. All right, the slight difference between these numbers is just in the rounding of the last digit. All right, so these would be the solutions for Form B. If you have Form A, this would be your answer. Form C, this is your answer, and Form D, this is your answer. All right, but the method for how you end up getting this particular question is going to be the same. You would do a crossbar to get the number of moles, and then you would end up plugging it into an equation, or you take that number of moles and you plug it into this. All right. Okay. So for the second question, this actually comes from version C. All right. So at pressure of 672 torr, all right, we have this many moles of a gas, and it occupies a volume of 30.4 liters. What's the temperature of the gas? All right, so this unit of torr right here, the one thing that you would need to know, and you can see this in the units for standard pressure, and that is that torr is just exactly the same thing as millimeters of mercury. So in terms of converting there, however many torr you have, you can just change that to millimeters of mercury. All right, I'll say a little bit more about like how you could convert between these units, but for this particular conversion, it's fairly straightforward. So 672 torr would be considered the same as 672 millimeters of mercury. All right, and so that's your pressure. We have an amount of moles of gas. We have a volume here. We don't know the temperature. That's what the question's asking us for. And as far as our R value, you're going to want to use the version that corresponds to millimeters of mercury. All right, taking our equation, solving for what we don't know, we get TL by itself, and then plugging the values in, we would get 53.5 Kelvin. All right, so the questions on this question on the other versions are similar. You might have a difference in the unit of pressure that they give here, but the answers would be are shown right here. For question 3, I'm going to use version D to give the solution. Calculate the pressure of a gas in millimeters of mercury, which occupies a volume of 545 milliliters if at 101.3 kilopascals it occupies a volume of 246 milliliters. All right, so this is one where you're basically saying there's one original condition of pressure and volume, and then there's a different condition of pressure and volume. All right, so I've gone ahead and highlighted this part of the question right here. If at 101.3 kilopascals it occupies a volume of this many milliliters. All right, so what that means is at the same point in time where this is the pressure, this would be its volume. All right, so that's what I'm going to go ahead and select as my P1 and my V1. All right, it's not necessarily that important whether you call it P1 and V1 or P2 and V2, but as long as you're saying that this number right here is the same as that, you're saying at this point in time where it has this pressure, at that exact same point in time, this would be its volume. All right, so it's asking us to calculate a different pressure, we'll call that P2, when the volume is this right here. So that's going to be my V2. All right, so taking these numbers and rearranging for the thing that we don't know, which is pressure. All right, so the pressure that we have here is 103 kilopascals, and we can go and solve, and what we would get is this number right here, but that number would be in kilopascals. Remember to pay attention to your units. All right, but we also know that there's this relationship. We know that if we wanted to, so the question is asking for the answer in millimeters of mercury. So we need to convert from kilopascals to millimeters of mercury. So this is essentially just a one-step widgets and gizmos problem. All right, so we know a conversion between these, and the place that we can get this information from is are all these standard pressure values. We know that 101.3 kilopascals is the same as 760 millimeters of mercury. So that allows us just to create this relationship. For every 101.3 kilopascals, that is the same as 760 millimeters of mercury. All right, and then it's just like a widgets and gizmos where we say, well, if this is our number of kilopascals, all right, we could just say, it's like you're saying, how many millimeters of mercury are there in 45.7 kilopascals? That's exactly the same way that we've done all of our widgets and gizmos problems. All right, so when you do this and do the math, it ends up turning into this number right here. All right, and again, pay attention to your significant figures. Notice that there are, of all these, 3 is the fewest number of significant figures, so that's how it should be rounded. All right, so version A would be 338. Version B would be, I think is the same problem as this one, and version C is 338. Okay, for question 4, this is from version A. All right, so this is one where you're given a volume, a pressure, and a temperature at one condition, and it's asking for a volume at STP. All right, so at STP, that would tell us a pressure and a temperature at some other time. So those would be our P2s and our V2s. All right, and it's asking us what our volume would be. All right, so the thing is, I chose 101.3 kilopascals as my standard pressure because my original pressure was given in kilopascals. All right, and that's going to make the math a lot easier. So since we have all three of these values right here, we can rearrange this to get what we don't know, which is V2. And plugging in the values, we would end up, what comes out of your calculator would actually have a lot more digits than this, but notice it's got 95 kilopascals. All right, that value right there only has 2 significant figures. So that means that your answer should be rounded to 2 significant figures. All right, and I believe that all of the answers on all of the versions had that same answer. Okay, so going to question number 5, this is coming from version B. All right, what's the pressure in millimeters of mercury exerted by this many grams of argon in a 24.0 liter container at this temperature? All right, so first of all, it gives us the gas in grams. All right, in order to do gas laws, we have to convert that to moles. All right, so the first thing I'm going to do is just say that for every 1 mole of argon, we have this many grams. Notice that the formula here is just AR, because argon is not one of those Brinkelhoff elements. So we do that and we figure out that that means 1.82 moles of argon. All right, the volume is 24.0 liters. The temperature is given like this, and you should realize we need to convert that to Kelvin since this is a gas law problem, and it's asking us for the pressure. All right, so let's solve for pressure. We would get this right here. Let's plug things in, and notice we have chosen this value for R because it asks for the pressure in millimeters of mercury. All right, so plugging that in, we end up getting this number right here, which is the answer if you round it to 3 significant figures, which is what you would do here. All right, the answers for the other versions can be seen here for A, C, and D. All right. And the last question is actually one that most people did just fine on. It's the one of Dalton's laws of partial pressure, which just states that the total pressure of a sample of a mixture of gases is equal to the partial pressures of all the individual components. All right. So we have a gas which is a combination of 3 different gases. We know what the total pressure is right here. And we can just say that that is going to be equal to the sum of all the gases that make it up. All right, and so it asks us for the partial pressure of carbon dioxide. And so if we just say that the total pressure is equal to the sum here, we could solve for what that pressure is right there. And then we could take, just plug the numbers in. The one thing I want to point out is that when you're doing this, remember, you're now subtracting, and this is a subtraction addition sig fig rule issue. So you want to take a look at these and look at the place of uncertainty of all these and find the one that's got the furthest left of those. All right, so this is the place of uncertainty for this one. This is the place of uncertainty for this first measurement and this one right here. So this position right here is the furthest left of all of those, which means that your final answer should be rounded at that position. So for this answer, it would be rounded to 0.148. Right? So for the other versions, here would be your answers. And that does it for this quiz. Remember, all of the questions between the versions are analogous. So the steps that I went through for your on your particular question might have different numbers, maybe have different units, but the steps that you would have to do should be the same. All right, so hopefully that makes sense, and we'll move on to something else.